Smashes the Gatorade on the table. Electrolytes everywhere. It's what physics craves. Okay, let's see what we got here. So we're looking at a AP Physics C mechanics problem from 2018, specifically question number 2. And we're going to be looking at a conservation of momentum, kind of force impulse thing going on here. And in this problem, we have a cart on the left, cart 1, is moving with some velocity to the right. It has some mass, and it hits a stationary cart that has a spring in front. We see the spring constant's 130 newtons per meter. And we're going to be asked a bunch of questions about it. So they're on a horizontal level track, no friction. That's very nice. Cart 1's got a sensor that measures the force on it exerted during the collision with cart 2. And it's got that spring attached. Cart 1's moving with a speed of 3 meters per second. And the cart 2 is at rest. Total mass of cart 1 and the force sensor is half a kilogram. Mass of cart 2 is 1.05. The spring has no mass. The spring's got a spring constant, 130 newtons per meters. And the data for the force exerted on the spring... the data for the force the spring exerts on car 1 are shown in the graph below. So we've got this graph here. This is the force that's the spring is exerting. And we see that the student fits this with a quadratic. This equation right here. That's going to be super important for us in a little bit. And we also have this kind of curvy thing. And oh, I'm a good curve. And really, if they plotted it with a quadratic, then it would really just be like a nice smooth function, right? So what we're asked to do in part A is using integral calculus. Calculate the total impulse delivered to the cart during the collision. Well, what we can remember just to begin with is that in general, an impulse is just a force multiplied by some amount of time. Okay? Now, with integral calculus, like this force times time works whenever you've got a nice shape, like a square, or a constant force like this. Because then we can just say, oh, it's this much force and this much, and that gives us an area. Except we don't have an easy shape here. We've got this quadratic. So really, when we're using integral calculus, what we can think about is this change of time here can be very, very, very small. It can be continuous. And that means that we're going to see for integral calculus that an impulse is going to equal the integral or the addition of many pieces of the force by some small segments of time. And what they're saying there is that for whatever force we have, if we take a look at a small piece of force and then another small piece of force, another small piece of force, another small piece of force, another small piece of force. I am getting annoyed with me saying a small piece of force. If we add up all of these small pieces, we'll get the entire area. And what integral calculus does is it makes these pieces infinitely thin so that we could draw an infinite number of them as we slowly shade in this entire region. But that's what's going on. Ooh, that was satisfying. So we're really just trying to figure out what is the area of this region here. We're not trying to figure out this area on the outside. That's not a thing because that graph goes all the way down to negative infinity here. We're trying to figure it out between the function that was made, this quadratic, and the x-axis here. Okay, so that's what we're trying to do. So to set up this integral, we want the force as time is ticking on. So let's put in our equation for the force. The student actually plotted that for us and has this value here. That's the 3,200 t squared minus 500 t. So our force equation is going to be 3,200 t squared minus 500 t dt. And let's see how long this is going for. It's going from a time of 0 to probably right about here, which is about 0.16 seconds. So let's go from t equals 0, our initial point, to a final point here of 0.16 seconds. Now, when we take integrals, this is a refresher if you haven't. These are a straight polynomial integral, and we're actually going to take an integral with dt with respect to both of these. In general, when we have an integral like t squared, what we're going to do is we're going to add 1 to that integral. So it's going to become, it evolves into t cubed, but then we need to divide by that exponent. So we're going to get like a t cubed over 3. We're going to ignore this constant and just place it back in. So what we're going to have for our first integral here, whenever we calculate it, we're going to get 3,200 t cubed over 3. And then we do for the second one minus, well, that's going to be 500, the constant. The t becomes t squared over 2. Okay, so that's what we have for that right there. Now what we need to do is we need to place in, and sometimes you'll see it written like this. This is impulse again. We need to put in our upper and lower bounds. So essentially, this is what the time equals, and we need to say it's going to be the upper quantity minus the lower quantity. So we're going to put in 0.16 for t cubed and t squared, and then we're going to put in zeros for both of these. When we put in the zeros, we get nothing out of that, so that's kind of nice there. But when we do this for the upper bounds, essentially we could write it out as 3,200 times 0.16 cubed over 3 minus 500 times 0.16 squared over 2. So that's the first part. That's the upper. And then minus, and then 0 for everything else. So whatever this is right here, whoosh, that's what our answer is. If we go churning that through a computer, oh boy, let's get a calculator up real quick. Da-da-da-da. That gives me negative 2.03. So my impulse here is negative 2.03, and my units of that are Newton seconds. They are a force times a time, Newton seconds. So whoo, that's just a calculator piece there. Okay. So yeah, we really just needed to take a little bit of an integral. This is a pretty straightforward integral, no natural logs or anything, just a polynomial. So we're good. For part B, we need to do two things here. We need to calculate the speed of car 1 after the collision, and then which direction does car 1 move after the collision. Okay, well, let's take a look at this. Car 1 has a mass of 0.5, and car 2 has a mass of 1.05, so this mass of cart 1 is less than that of 2. But cart 2 isn't moving, and cart 1 is. So maybe we get an intuition that cart 1 is going to bounce back, but maybe we're unsure of that. So let's just hold off on that for a second and see what's going on here. But my gut's telling me that it's going to bounce back. So let's see what's going to happen. To find the speed of cart 1 after the collision, what we need to be able to say is that, hey, look, this impulse existed on the car, and that impulse was negative 2.03 Newton seconds. We can say that that impulse is equal to a change in momentum. And remember, change in momentum is the mass, and we'll call that cart 1, by the change in velocity. And remember, a delta, a change, is always a final minus initial. So this is like m1, and then cart 1 final minus cart 1 initial. And now it's just a matter of plugging in numbers. So we know that negative 2.03 equals 0.5 times the final, which we don't know. So we'll just call it V1F, minus 3 meters per second. Okay, and in this case, since we said minus 3 meters per second, what we actually just implied here was that going to the right is positive and going to the left is negative. Okay, because we said that V naught here to the right is 3 meters per second. So now we just have to solve for the initial velocity here. When we do this, we could divide by 0.5, so divide by 0.5. That gives us, oh, what is that? Negative 1 point something. Excuse me. That's negative 1 point, we'll just call that 0.1 for now. Our calculator will get it later. And that equals VIF minus 3, or V1F, excuse me, V1F minus 3. And then we can add 3 to each side. That'll give us, what is that, about 2? Does that seem about right? Oh no, I just messed that up. Woof. I just messed that up. Silly math. When I divided by a half, I took half. I didn't divide by half. Dividing by a half is like multiplying by 2. Whoops. So that left side is actually going to be negative 4.06. And then we're going to add 3 to it. So our velocity of mass 1 is going to be about negative 1.06 meters per second. Ugh. That's what we wanted. We divided by a half. That's like multiplying by 2. That should be a 4. Oh boy. Okay, so that's what we found for the velocity here. Is it going left or right? Well, our gut told us left. That negative sign right there also tells us that it's going left. Okay, so there's our velocity. It's about 1 to the left there. For part B, what's the speed of cart 2 after the collision? So we can do the same thing here. We can look at that impulse giving us a change in momentum. Oh boy, it's early. It's early this morning. So that impulse is giving us a change in momentum here. The thing we have to be aware of this time is that for our impulse momentum, our impulse is going to be in the opposite direction. So this impulse up here we found is negative 2.03 Newton seconds. That was the amount that the spring exerted on cart 1. Well, we know we're going to get equal and opposites there because impulse momentum has to be conserved. So what we need to be able to say here is that the negative impulse that we have is going to equal that entire same change in momentum. Another way to do this, and the way that I kind of like doing it a little bit better, is just to straight up conserve the momentum in this problem. The way I would write this is I would just say that, look, the initial cart, its momentum, m1v1, plus the momentum of cart 2, but since that velocity is 0, it's going to be 0. That's just equal to cart 1's final velocity, because that's an initial, plus cart 2's final velocity. Okay, so final momentum values there. And now I can just go ahead and solve this for this cart 2 right here. I know that the mass of cart 1 is 0.5 and its initial velocity is 3. I know that its mass hasn't changed and its initial velocity is negative 1.06. I know the cart 2 mass is 1.05, and now I just need to solve for the cart 2 final. Like, I think that is way easier than trying to think about negative impulses and forces acting on other things. This is just right there. It's just a conservation of momentum problem. So if we go ahead and math this out just real quick, that's about 1.5. This is going to be equal to, what is that, about 0.53 plus 1.05 V2F. Subtract the 0.53 from each side, so we'll just get rid of that. So we've got about 1 equaling 1.05 V2F, and this is just kind of sloppy, but I'm just kind of running through it. Did I do that right? Oh, no, I didn't. I messed something up. I was like, that's only going to give us something under 1. That doesn't make any sense. This is a negative here, so that's a negative there, so that's a positive. So this is going to be 2. So we're going to have 2 equaling 1.05 V2F. That's going to give us something closer to around 2. It's going to be just under that. And when we divide by the 1.05, we find that V2F is going to equal, oh, what is that? What is 2 divided by 1.05? 1.9? About 1.9 meters per second. We see that's a positive number, so that this thing's going to the right, which only seems to make sense because if it's been hit by something, it needs to start drifting this way. So that kind of makes sense there. And that's a good value for what we have. Man, that's 2 sign mistakes I've made this far. Oh, pay attention to your signs, children. Okay. We also need to show that this collision between the 2 carts is elastic. So let's get some space going over here. So elastic. Well, we know that a collision is elastic when the initial and final kinetic energies are equal. Inelastic collisions lose energy. There's some sort of deformation, like a bumper breaking or the clay deforming. But if we can show that the initial kinetic energy is equal to the final kinetic energy, we'll see that we're elastic here. Okay, so that's what we're trying to prove. So let's just write this all out for the kinetic energies. We're going to have the initial kinetic energy of cart 1 is going to be a 1/2 the mass of cart 1, the velocity of cart 1 initially, plus the same thing for cart 2. Luckily, cart 2 wasn't moving, so that's going to be a 0. Then equals 1/2 the mass of cart 1 times cart 1's final plus 1/2 the mass of cart 2 times cart 2's final. And when we put some numbers in here to solve, we're going to get 1/2 times 1/2 times the initial velocity of cart 1, which we had was 3 meters per second. Oops, you know what I'm forgetting? Squares, squares, squares. Kinetic energy is 1/2 mv squared. Squared. This is equal to 1/2 times 0.5 times the final velocity of cart 1, which we had is that negative 1.06. That's really not going to matter because we have to square this problem, plus 1/2 of 1.05 times the final velocity of this, which is like 1.9 squared. Oh boy. Okay. So let's just get numbers for everything and see what happens here. 1/2 of 1/2 is 1/4. 1/4 of 9 is 2.25 because we do 4.5, 2.25. So that's going to be 2.25 joules because we're in energy here. That's going to equal, oh, this is not fun. Where's the calculator? Okay, so 1/2 of 1/2 is 1/4. 1.06 squared divided by 4 gives us 0.28. And then 1/2 of 1.05 times 1.9 squared gives us that, and then the 0.2809 gives us 2.24529 joules. Those are about equal. So since those are about equal, I can say those are elastic. If they were vastly different, then well, I should say about there because they're not exactly equal. But since they're about equal there, we can call those elastic. Because remember, an initial kinetic energy and a final kinetic energy being equal is how we determine elasticity. Or rather, if something is elastic. Elasticity is a little different. So yeah, those are about equal. We have an elastic collision. I take it. Last part here, probably the harder part of this. Calculate the speed of the center of mass of the 2 cart spring system, and then calculate the maximum elastic potential energy stored in the spring. Oof. Okay, so what we can say is this. For our center of mass for the system, we need to start thinking about both carts, M1 and M2, as being together, okay? And what we can say essentially is that the momentum I have in the beginning is the momentum I have at the end. So I can say that the momentum M1 V1 initially, that has to equal the momentum of everything in the end. And the momentum of everything is both masses combined and then the center of mass of that system, okay? So that's a way we can think about a center of mass here. Instead of splitting this and looking at M1 and M2, we're saying, look, let's take everything together and then just look at the center of mass of that. So this is just a quick little thing to solve for. This gives us that the velocity of the center of mass here is just going to be M1 V1I over M1 plus M2, and that gives us half times 3 over half plus 1.05. And this gives us a quantity that's about, let's see, that's like 1.05 or 1.5 divided by 1.55. So 1.5 divided by 1.55, that's a little less than 1. Let's churn that through real quick. 0.97 meters per second, positive value. We're going to the right. And if we want to calculate the maximum elastic potential energy stored in the spring, we've actually got two ways to do this in this problem. I think one of these methods is a little bit easier than the other. It really depends on how you want to think about it. I like to think about the fact that if you were to take a derivative up here and set it to 0, that would give you the maximum force applied by that spring. And if you know that F max, you can just use it and set up a 1/2 kx squared. I like to just do it like that. If you don't like to do that, that's fine as well. There is another way to do it. But that's the way I like to do it. We would basically solve for k here. Well, we would do this. If you want to do it this way, you'd solve for F max. And if you wanted to, you could just approximate it here. It's about -20. But you'd use this equals kx. And you'd solve for x here. It equals some number. And then you go ahead and you'd say that the stored spring energy equals 1/2 kx squared. So you'd get this value first, and then you'd get this value second. You can totally do it that way. That's the way I like to do it. If you get F max just by saying, hey, look, it's about -20 here, that's fine. The other way to do it is to say that df dt equals 0, and we essentially just take the derivative of this and set it equal to 0 and find a time. When you do that, you would find that your time here is about, it's like under a second. It's right around in here-ish. It's 0.078 seconds. You use this time and put it back into this equation here to solve for the force, and that gives you F max. So there's a little bit of math to do if you do it that way, but if you feel comfortable with your derivatives again, and setting things equal to 0, and then kind of going F max equals kx, solving for x, bumping x into 1/2 kx squared, you can do it that way. Nothing wrong with it. That's the way I like to do it. Other way you can do it goes like this. So we'll come back down here. You can say that the conservation of energy has to exist for a elastic system like this. So we're just looking for the elastic potential energy stored in the spring. So what we can say here is that the initial kinetic energy we have has to equal the final kinetic energy plus that spring energy we have there. So, and we can think about this for a center of mass system. So what we'd say here is we'd have 1/2 m1 v1 initial squared equals, and then this is the comm system, the center of mass. We'd have to say this is 1/2 m1 plus m2 times v center of mass squared, and that added with our spring energy will be everything there. So it's just a matter of adding all of that together. When you do this and you plug in all of your numbers here for what we found for vcomm and everything else, we see that we end up getting a spring energy that's stored of about 1.5, 1.51, 52 joules. That is the same as what you would get above if you did the derivatives. You might get a slightly different number if you did it the way I prefer above. If you did it this way, just because if you estimate where this is in the graph, maybe you call that -20, maybe you call it -21, -20.5, I don't know. You're trying to pick something in this region, which may give you a slightly different answer, but showing all your work and having everything there, you'll still get full credit for that in that solution set. Both ways are totally fine there. Okay, so with that, a mechanics problem. This is a kind of bigger one. There's a lot of stuff going on here, but nothing too crazy with the calculus other than one integral in the beginning, and just conserving momentum over and over and over and over and over again allows us to finish this problem. Take it easy. Adios.